Everything we've done so far in chapter 5, all of that was for the section 5.1. So now we're going to move on to looking at section 5.2, which is on congruence. So congruence, this is one of the most important relations on Z. So 5.1 was looking at relations in general, trying to understand what are these. And now we're going to hone in specifically on this relation of congruence. So we're going to get some motivation. So we're going to think about clock arithmetic. Some of you may have seen clock arithmetic back in your maybe elementary, middle school, high school days. Maybe you haven't seen it, but all of you have done this in your head. So if you think about this, if you're at 11 o'clock and you add on 4 hours, what time are you at? Well, if you're at 11, add 4 hours, this is going to be putting you at 3 o'clock. Now, if you're at 8 o'clock, and then you add on 6 hours to that, you think, okay, so if I add 6, to what time am I at? Well, this is going to be 2 o'clock. So what you're doing is you're adding, but you're adding things in a different way than you've added before, right? Because at 11, you add 4, well, that should put you at 15, right? But all of a sudden, instead, you're at 3. Same thing here, 8, and you add 6 to it, then that should put you at 14. But instead, that puts you at 2. Okay, so this clock arithmetic, this is going to motivate this idea of congruence. So if we think about what's going on here, what we're saying is that we have 11 plus 4. This is equal to 15, but it is 3. So this 11 plus 4 is 15, but instead we're actually saying that that's equal to 3. And then this one, we're saying that we have 8 plus 6. Well, we know that that's equal to 14, but instead we're saying that it is equal to 2. Now, obviously, you're all very well-skilled mathematicians. You're like, well, obviously we know what's going on, right? We can't get bigger than 12, right? 12 o'clock is the largest that we get. Once we go to 13, we go back to 1. Yes. So what's happening here is that if we look at this case, if we try to do 12 goes into 15, what we get is we get a remainder of 3. Right, 12 goes into 15 once, but there's a remainder of 3. Similarly, if we look at this one, if we again divide this by 12, well, what we get is we get this remainder of 2. So this idea of congruence, we're not so much studying quotients or anything. We're really studying remainders of one thing in relation to the other. So congruences, we should be thinking of remainders. So this is the formal definition. So if we have n is going to be a natural number, remember natural numbers, these are things like 1, 2, 3, 4, and so on and so forth. It is not including 0, and it is not including negatives. And then a and b, these are going to be integers. We're going to say that a is congruent to b modulo n. So this idea of being congruent modulo a number, this is the definition. And so what this means is that we're saying if a minus b is equal to k times n for some k in the integers. So what this statement is saying, a minus b is equal to kn for some multiple of n. We're saying that if you subtract these two, you get a multiple of this natural number. So we're not ever going to be looking at modulo -3. We're always going to be looking at modulo, say 2, modulo 7, those things. So this notation we're going to be using a lot is A with this 3-lined equal sign. A is going to be congruent to B. So this is right as A is congruent to B mod n. Or you could say A is congruent to B modulo n. But this is what we're looking at. So what we see in this case is that we saw that 3 is kind of like 15. And in this case, 2 is kind of like 14. And what that means to be kind of like is, again, we're looking at these remainders. So what we see in this example is that we see that 2 is going to be congruent. 2 is going to be congruent to 14 mod 12. So this example here of 8 o'clock plus 6 hours is 2 o'clock, this is really saying that this is true. And so what this statement is saying, using this definition, is we see that 14 minus 2 is equal to 12, which, for this to be true, we need to have 12 as our natural number. That needs to be multiplied by some integer to make this true. And indeed, that integer would be 1. So this satisfies the definition of 2 being congruent to 14 mod 12. And then also this first one we looked at is that we see that 3 is congruent to 15 mod 12. And again, this is because, oh, my apologies, I subtracted these in the wrong order. This should have been 2 minus 14. Sorry, 2 minus 14. This should be negative 12, and so this is going to be 12 times negative 1. So the same thing here. We're taking a minus b, so we're going to have 3 minus 15. That's going to be equal to negative 12. And again, we're wondering, is there an integer that I can multiply 12 by to get that? And indeed, that integer is negative 1. So this is true. We have that 2 is congruent to 14 mod 12. 3 is congruent to 15 mod 12. We could then ask some other questions about other numbers. If we look at other types of bases here, we could say, so other types of natural numbers, we could ask, say, is 3 congruent to 23 mod 7? So we could ask any numbers now that I want to throw out here. Is 3 congruent to 23 mod 7? Well, if this is true, what this means is that there must exist an integer that makes this true. So we're asking, is there some k in the integers such that I take 3 minus 23 is equal to 7k? So this is the statement I'm asking. Is there some integer k that makes this true? Well, this becomes a negative 20 is equal to 7k. Is there some integer k that this is true? Well, no. So this is not true. 3 is not congruent to 23 mod 7. But then if we look at a different example, we could ask, say, is 21 congruent to 5 mod 2? So again, the statement, is this true? Well, again, we're trying to rewrite this using the definition. So we're wondering, does there exist an integer k such that 21 minus 5 is equal to 2 times k? So is there some choice of k? Well, this statement here, this is saying 16 is equal to 2k. Does there exist an integer k? Well, yes. You could now consider k is equal to 8. So this statement is true. 21 is congruent to 5 mod 2. Now remember, I said that this is related to remainders, right? So if we look at the remainders, the remainder of 21 if we divide it by 2 is 1. The remainder of 5 if we divide it by 2 is 1. The remainder of 2 if we divide it by 12 is 2. The remainder of 14 if we divide it by 12 is 2. The remainder of 3 if we divide it by 12 is 3. The remainder of 15 if we divide it by 12 is also 3. The remainder of 3 if we divide it by 7 is 3. The remainder of 23 if we divide it by 7 is 2. So this is exactly The idea behind congruences is that if you have the same remainder when you're dividing it by this number, then they're going to be congruent. If you have different remainders, like in this case, you have different remainders if you divide by 7, those are not going to be congruent to one another.